Alright, so welcome to video 2 on how I'm building the 4coder Lexer out of a structure modeling system. The first stage of this is going to be some optimizations, and by optimizations I don't mean optimizations of the generator code, I mean optimizations of the model that are done automatically. So before we get into that, I do want to do one quick. I detected the possibility that there might be a bug while I was going through the previous video. A bug in particularly how I'm handling the period operators. And I just want to make sure that I've thought this all the way through. So main ops with dot are all of the operators that begin with a period. And when I create that operator set, what I do is I first say I remove everything that doesn't begin with a period, and then I say I remove the first character of every operator. And if I do that, the dot operator needs to get removed. So, okay, I think this will work. So I was worried that this thing here wasn't going to be able to handle an empty string, but if I remember correctly, when I do string skip, that actually... yeah, so that requires that when it's doing the string skip, it's skipping like one character in this case out of every lexeme in the set. And if it turns out that it's going to skip past the end of the string, it's going to make a string that's empty by doing that, it just doesn't even keep it in the set. So the set just loses it. So this doesn't even have the period in it as an empty string, whereas it does have like dot 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 as dot dot because the first dot gets removed. And it has dot star as just star, and that's the way it should be. It's correct because I intentionally wanted to go from this here to this, right? Basically that. The set of continuations off of a dot is what I got by doing that. And then down here, where I have, the operator or f number dot, if I see anything that can be the extension for an f number, so if I see a dot followed by any of these, that can be an f number. If I see any of the characters from that set, so if I see a dot or a star basically, which is not written out explicitly here because it's being derived from this set, so that I don't have like this information needs to be cross-referenced with the information in my operator set. If it sees any of those characters, it goes ahead and does this. Now, I didn't actually go into explaining exactly what this is, but this right here is like a helper type that is in the operator class. And the reason it's in the operator class is because it basically takes in one of these sort of like helper models, in this case the operator set, and generates a state machine from it. So I can like manipulate my operator set with these like the different operator functions here, and then I can also use the operator set to get a character set, which is like in this case the dot and the star. In the case right here, it's the like all of the things that an operator can start with besides these three things. And then I can also use the operator set to generate the entire state machine. So you can see I'm using that here to generate a Lexer state machine from the operator set that we built with dot there, the with dot portion of the operator set. And this builds a operator parser that works with everything that doesn't begin with a dot or a slash, right? So that, is just a handy thing to have around. I put in an operator set, I get out a state machine that parses that operator set. Done. Don't have to think about how it happened. It did the modeling and now it's done. And it doesn't take too long, so everything is good. So, point is, after I run this, I have called build language model, which this file here had to define. So the next thing I really want to do is I want to look at the model and simplify it. And I want to simplify it in particular ways. The most important thing is I need to move first all of the action lists that exist for state entry. So all of the on entry actions need to get zeroed out. These need to be gone. And they need to be moved into the transitions of states. But before I can do that, it might pay off to do some other stuff. Doing that will basically spread out these actions everywhere. But before I do that, I might be able to like shrink down my sets a little bit here. So I have a set of states, and each state has a set of transitions. We can actually simplify both of those. So we could simplify all transitions, and then simplify all like transition lists, and then simplify all states. Now, it kind of matters what order we do this in, because the way we simplify all states is we start from the root, and we are going to read all the transitions that our current state has. For each of them, every state we visit in this process, starting from root, get marked as needing to be kept. And so we will go through all of them and say, like, okay, look at all your transitions. Where do you transition to? Look at all your destination states. All right, if you have that destination state, it's possible to go to that state. So mark that state and then add it to the queue. And then later it'll get popped off the queue, and all of its transitions will get marked. And eventually we will have marked everything we can reach. And then anything that's not marked gets removed. On the other hand, if I do that, it's possible that some of these transitions would have been simplified out. So what I could do instead is say, let's go through all the states. We're not going to simplify out any states. We're just going to simplify out all the transitions. Now, how do we simplify out transitions? We basically look to see transitions, their order matters, because if I have two transitions in the same, like two transitions whose conditionals overlap, it's possible that the first one will always be the one that actually operates and the second one never does. For instance, if I had two fallbacks in a row, the first fallback would always catch it, the second fallback would never happen. But there are other cases where this can happen. Like, I can go through the transitions and say, hey, I have a transition here that says whenever this flag is set and the input is, you know, this character, do this. And then later I have a transition that says whenever the input is this character with no flag check on it at all. But that can only happen if if it's this character that we're getting input and the opposite of whatever that first flag check was. But then before that, I have a fallback that works whenever that flag check is operating, and so then I could notice that, hey, there are no cases where this transition is possible. Either the flag is set and it got handled in this case, or it's not set and it got handled in this case, right? And so there you go. Now, doing the full calculus to fully simplify those down is kind of intricate. There's a lot we could potentially have to work through to prove that a transition is not reachable. But if we do that first, then we will get our simplification of states will be better. If we do it first, though, that means we will have to do it on all the transitions, even if some of those transitions are on states that we could have already simplified with unsimplified transitions. So we could go as far as saying, let's simplify all states, simplify all the transition lists, and then simplify all the states again. Then we would have gotten the simplest thing I think we can possibly get. But we could also do that by doing this. And the question is, which one would be faster? And I think the answer is this one will be, because if we're generating states that literally are not connected, that is possible because we have operator things that fill in states that are potentially then not used, right? It's possible that we are creating states and then never actually connecting to them, because not because we by hand wrote a state and then didn't use it. Although it is possible that we declared a state in that list. Remember, there's this thing, right? State. Right, there's this whole thing here, so it's possible that there are just states floating in here that aren't real, that never actually get used, that I needed at one point and then removed, but didn't remove from here. And so that, will be a little bit of extra work if we don't simplify those out first. But it's also possible, and more likely, I think, that these things here that generate a set like partial state machines for particular operator sets, things like this that are generating states might become more common. And I'm not sure that this one necessarily generates states that are not being used, but there's no reason to assume that that'll always be the case. In fact, in other state machine models I've written, it's very useful to have states that you'd end up not actually connecting to. And so I'm just anticipating that that could be a thing that happens a lot. But right now it's not happening at all. And if we do end up needing to simplify states twice, I think that's just going to be a matter of copying a function call up there. And so I think this is the optimal way to do it for now. We don't need to do anything fancier than this. So once we've done that, we will have only the set of states that is relevant, and each state will have only the set of transitions that are absolutely needed to implement that state's entire behavior, and none of the extra ones. Then when we do this, we will have only copied around actions that are actually necessarily a part of the definition that we're going to use, right? But then we're still not done, because that doesn't do the optimization of the consume. So what we basically want to do is optimize out all action lists, or optimize all action lists that don't contain a consume action, right? So any action list that doesn't contain a consume action, that needs to get optimized. And I talked about that a little bit before, but basically all those things that are doing peaks can be optimized by looking ahead at what the next states would do if, you know, if they got the input that we are currently writing code for, and in that way we can extend out all of the actions lists to do the right thing. Now that could get fairly complicated, because a transition case that says, like, look, if you see any of these characters, then that's a peak, and don't consume it, and then transition to that state and let it consume it. Well, the problem is, it might be that that state will handle some of those characters one way, and the other side of those characters another way, and another side of those characters another way. So what used to be one transition might have to break up into multiple transitions. This is a fairly intricate optimization, but I think it's going to be worth it. Once we've done all that, that's like the condensing and simplifying. This is like simplifying the state machine. The next part we want to do is we want to figure out how we're going to do the code generation itself. Like, what is the actual output? Is it going to be a hand roll, like a control flow based state machine in the C code, or is it going to be a lookup table accelerated state machine in the C code? And if it's going to be lookup table accelerated, how are we going to isolate the state machine into smaller state machines that keep the table size down? So this is basically state machine generation. So in there we're going to have to answer the question, how do we isolate the state machine parts into small lookup tables? Generate tables. Generate as one big control flow based state machine. Right? We also want to ask ourselves, what features does the generated code need to support? I might want to have like a fast full input version that just says, here's the whole string, this is the entire file, just go to town, lex it as fast as you can. Then I might want to have like a re-entrant slash resumable, like a resumable lex fed chunks at a time. And I might want one or both of those, and I have to decide which ones I want and figure out how the implementations need to be altered for those features, right? So that's all stuff that we're going to have to do over the series of these videos. So it's time to actually start doing some of this. Step one, let's see if we can write the code that simplifies a transition list. So this can go right here. Internal void. Essentially what I want to do is just start sticking these things in right like here. So we have the root. We also have the primary context. That's what I'm going to do first, is I'm going to grab the pointer to the primary context. Whoops, Lexer primary context equals, that's just going to get pulled out of right there. And, okay, so what we need to do is say, yeah, so in addition to having the root, we also have the state set, which lets me just iterate all the states. So that's what I'm going to start with, is I'm just going to go give me each state in the state set. Okay, so I'm looking at each state. Each state has this transition set. That should really be called a transition list, I think. Yeah. So I call it a list if its order matters, and a set if its order does not matter, just so you can keep up with my mental process there. So this will be called the transition list, and we'll get it as a pointer off of this. Maybe I'll just call this transitions, right? And the point is we want to, when we're looking at these transitions, determine if a transition is redundant. Now how do we do that? Well, basically what we need to do is for every type of input, so every value between 0 and 255 and EOF, so we need an array of 256 things, 257 things of some sort of thing. We haven't determined what sort of thing yet. And each of those things that I haven't determined the type of yet needs to keep track of if, like, it could be a set of booleans, like, is this particular input handled? But I also have to check, is this input handled in the situation where this flag is 0 and where this flag is 1? So, the full matrix is that there's a handler for every possibility of basically for every value in E and S. Now I have over here, I moved it off screen, but remember E is my alphabet, so every value of a byte and EOF, and S is the set of all possible flag fields. So if every state needs to have a full definition of what it does to handle every possible case, and every possible case is defined by the set of all pairs of inputs with state fields states, right? So how many is that? Well, that's 257 times, and in this case, for instance, I think I have 10 flags, right? Let me go read how many I have. 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 flags. 1, 2, 3, 4, 6, 7, 8, 9. Yeah, I have 9 flags. So I have that times 2 to the power of 9, right? So how big is 2 to the power of 9? Well, 2 to the power of 8 is 256, so it's 512, right? So that's how many I have in this case, how many states I have to cover. So I need a bit for each of those. Let me see if that is a reasonable way to look at this problem. I need a calculator. So number of characters in the alphabet, number of state or bit strings that represent my flag states. That many bits, I would need 16 kilobytes to represent every possible one, and so then on every for every state, I would start with a 16 kilobyte thing that's zeroed out. Now the problem is it's not actually that simple, because I still haven't answered the question, one, how do I determine the size algorithmically, because the number of flags will change from machine to machine. 2, that reminds me, we also want to simplify flags at some point. And if there are redundant flags, it's going to make this much slower, so it might be worth it to say simplify flags first. I don't know. But certainly we want to simplify flags at this point, because we won't have, like, the optimization of the actions will affect what flags are actually getting used, so that's probably a good way to do it for now. I mean, like, the most correct way to do the simplification would be to say something like, let's do this in a loop, so do all these things, and as long as the changes happen, go back here and do them all again, and keep on doing that until you've simplified and done a complete simplification pass that didn't change anything. Although, it would actually not quite be like that, because this only needs to happen once, so it would actually be more like, I don't know, maybe this gets looped. Until it does, until it's like no longer achieving anything. We might also want to throw in there like remove redundant states, or simplify states. Simplify states, optimize states, right? Might be something like that we want to do, not sure. But I'm not going that far yet. Right now I'm just saying let's figure out how to do this. Point is, not only does that need to be figured out, but I just calculated this based on the number of bits I needed, And so that means I would actually have to have an entire way to index into this thing, right? I did divide by 8 because I was talking about how many bits I need, but if I do this, it's 131 kilobytes, and that's going to be a lot easier to write the code for because I don't have to do any bit indexing, which is going to be tricky. So I have to think about this for a little bit. What is the best way to structure the data structure that represents which things have been handled? So an alternative to what I'm saying so far is I'm just assuming that it's like a single Boolean for every possible case, right? But a lot of times a single case like handler is handling a bunch of those because we have most of the time a case handler doesn't care about the flags at all. So in that case, there's like 257 types of inputs. It might even have a bunch of inputs. So it's like one state handler in there says, I cover all of these things, right? And so what might be more useful is to say, for a given transition, can we create a succinct list of cases where, like a way of representing the set of cases that this particular transition can be triggered by, and then iterate through the previous transitions to see if any of them are still available, like on the fly, rather than trying to remember. I guess another way to do this, I guess I see a way to do this. Okay. So the way we're going to do this is whenever I'm defining these things, right, these transitions in particular, I guess. So let me show you this. I'm going to show you this way. I'll show you this way. So I'm saying that it's a matter of check the entire flag state, but actually there's a simplification here because no transition's allowed to have more than one flag check in the current modeling scheme. I don't have like arbitrary, this function here can't be fully, I can't implement every possible version of this because even though I am allowed to use S to determine Q, depending on the current state and the current input character, only one of the flags in here will actually matter. Which one it is depends on what the character is. I see. Yeah, so what we really want is a thing that sort of represents whoops, don't do that. Here's the optimizer. And it's going to have basically like case description thing. And a case description is going to contain a U16 that represents the input, right? That's for everything that a byte can represent plus the EOF, which would be one pass, what the highest thing a byte can represent, I guess. And the potentially which flag and the state of the flag that case description represents. So that's just flag and flag value. So if flag is null, then we know that this covers all possibilities, right? So then it means that it means like anyone who uses that input without a flag is later with or without a flag. Anyone who's trying to get that input is already covered if this is null. If this is not null, then you are only covered if your input matches the input and your flag matches the flag value here, right? So now the problem is, what am I going to do if I have like a transition with 1,000 inputs, right? 1,000 inputs is too many. If I have a transition that has like 50 different possible inputs that can trigger it, or worse yet, a fallback one that can be any input, how am I going to represent that here? Well, I think what I need to do is I need to say, okay, we're actually talking about an array of possible inputs. So let's call it like this. Or, you know what, better yet, I already have this up here, transition case kind. Why don't I just say we're going to look at this. Now, ignore, by the way, the lim match. That's something we're going to do separately because it's a whole complicated ball of unoptimizable, untouchable nonsense that'll be trickier and harder to deal with and everything else that was completely necessary for raw strings. So there's like case kind, and then we'll just put the string in. That's how we'll do this. Right? So this here is everything we need to know about the case description. And actually, flag check, case kind, yeah, if I were to move this is a bit of a weird way to write that, like that, and then restructure this like this, you would see that this is actually this, right? So why don't we take advantage of that and say that there's like this concept of a transition case, and then rewrite this as just the like condition or something, right? It's going to require me to rewrite some code, so let me, whoops, wrong compiler. Bloop, bloop, bloop. Condition dot. But this is going to be better, because now my language for discussing overlapping conditions and my language for describing a transition which has a condition on it will match each other, so that I can do something like this. For each transition, I want to take the current transition case, I'll call that like this, right? And then I'm going to say, do a loop that starts from, whoops, that's wrong. Okay, so I see what's happening. I did this wrong. So this needs to be a loop of transitions that goes over the entire set of transitions, and then I grab the condition out of the transition that I'm looking at, and then what I do is I say so what I'll probably do is I'll build like a new first, and because I'm gonna try to eliminate some of these as I go, right? So I need a new like linked list right here that I can finally assign to at the end. And in the middle, what'll happen is one of these thingies where you grab your pointer ahead of time so that you can put this into the new list if you're keeping it. And then what we'll do is say, okay, grab a condition, and then say do a loop over, and what are we looping over this time? It's transitions again, but this time it's the new transition. So I'll do this like prev trans equals first, and so the first time we go through this, we won't actually have anything in that loop, right? This loop will start off as never iterating anything because first will be null and it'll immediately end right here. The first case is always covering something that hasn't been covered yet, so that makes sense. But what we'll do is we'll say update the condition. So condition equals like we're gonna call this like optimize or something. I'm just gonna say opt is the prefix for optimizer code. Optimize, and we'll call this like condition Eclipse. So I take the condition that exists inside this guy and I eclipse it against this to get a new condition. The condition that has everything this condition has that wasn't in here, right? So this eclipsed by this. Okay. If I get to the end, so I'm going to want to add a new case kind, which is like case kind none. And that's not valid, so none of the case transitions that I generate should have it. But I might want that to represent that this condition failing, right? So if condition dot case kind equals transition case kind none break, and then if we get to the end and the condition case kind is still not none, then we will know that we need to insert this into the new list. So the transition we are looking at that is a part of the old list still will get inserted into the new list. Okay, so now that'll work the moment we have the ability to do this Eclipse condition thing. This, I don't know what to call it. So, bloop, I just want to have those side by side. And this version of 4coder doesn't have an easy way to like sync the two views up at the same position. Alright, and the reason I want that is so that I can go like this. So, down here, the code I want to grab is that, put it up here. Internal transition case Eclipse, because that's the name of the type. So I'm going to say transition case primary Eclipter, and now the question is, can we define a way of transforming this based on this? Let's take a look. So now I'm going to pop this over here to this so I can see everything this can be. And what I think we want to do here is we want to switch on the primaries kind, like that. We're going to eventually return primary in its modified form, if any modifications happen. So we're switching on that. Okay, so now what we're going to do is for each of these, we're going to say, if this is the type of thing I am, then I need to look at Eclipter to see what it is, to see if it eclipses me. So, first of all, I am only eclipted by something if our flag checks, if our flag checks, like, if its flag checks eclipse my flag checks. So that's something I can do before I even do this part. I can do flag checks, non-overlapping flag checks equals false if primary dot flag does not equal 0 and Eclipter dot flag does not equal 0. So I'm looking at two different things that both have a flag. Then if this flag here does not equal this flag here, or my flag values do not equal each other, then I have non-overlapping flag checks. So if I have non-overlapping flag checks, then I don't need to do anything else. Primary can't possibly overlap with Eclipter in any way that is reducible, right? It might be the case that if I did analysis on the flags themselves, I would discover that, oh, this flag, you know, and that flag are different from each other, but if this first case ever is false, then the second case has to be false too for this particular provable reason. I'm not going that far. I'm just saying if we have redundancy that is, like, clearly an obvious redundancy, then we're going to optimize that out. And I'm saying that because I know there are places in the algorithmically generated portions of the state machine, the stuff that comes from right here, right, I have this algorithm here that generates part of the state machine algorithmically, and this can do all kinds of stuff. It puts multiple fallbacks in potentially to make sure things are happening. It just is a little bit sloppy. This code generation here is being a little bit sloppy and expecting this optimizer here to clean up a few of the things it's doing that are redundant before it goes to the code gen stage of optimization. It expects someone to do some cleanup on those transition cases. So we need to do this, like the dumb part. The smart part, you know, maybe is worth someday, but that's like low-level optimization stuff, not this basic stuff that we're trying to do here. That's like if you really want to get serious about making this thing as good as it can be, which I don't need it to be the 99% thing. It's going from more like 95%, 90% solution. Okay, so so yeah, in this case we have non-overlapping flag checks. If we don't have non-overlapping flag checks, or rather what I should say is, let's flip this whole thing. So if we do have overlapping flag checks, then we need to do this part. So here we make no modifications, nothing's happening. But if either of these doesn't do a flag check, or if they both do a flag check that happens to be the same, then we need to look at this part. And now we can ignore the flag part because it no longer actually has any bearing on how we transform the rest of this. The rest of this is going to be a transformation of these things here. So, if I'm a character array, and the thing eclipsing me is, well, there's a couple things it could be. If it's a character array, or an fallback, it's interesting. If it's either of these things, it's not interesting. In fact, if it's this thing, it's an error. So switch eclipter case transition case kind. So if our eclipter's case kind is a character array, we have one thing to do. If it's a fallback, we have another thing to do. I'm not going to even touch these. This is going to get like type checked or something later, and this just it has no interaction. If I'm a character array and the thing eclipsing me is an end of file handler, then it doesn't alter me in any way. But if I'm a character array and it's a character array, then any character I have that it also has, I need to remove from my set. So basically, I need to do like primary dot yeah, we're gonna have to do like a character replacement thing or something. Primary dot what do I call that? Case characters equals string. I don't think I actually have a thing that does this. This is a fairly unusual operation, but it would be like string character set subtract, right? And so I'm subtracting this guy's characters from this guy's characters. And if, in so doing, the primary character's dot size becomes 0, then the primary case kind has just changed to none. There are no situations in which we can transition into this now. Similarly, in this case, it's always just it's done. If a fallback came before a character thing, then it's done. Okay. What if I am an end of file character? Well, in that case, let's see, it's going to be kind of similar to this, except that it doesn't need to do all this. If the thing eclipsing me is a fallback, then I'm done. And if the thing eclipsing me is an end of file, then I'm done. If I am a fallback, then I am only eclipsed by other fallbacks. And so we can just do this by taking this and going boop. If I'm a fallback and you're a fallback, then you've eclipsed me and I'm done. Finally, delim match, we don't really want to touch that one. So basically if we are if I am a delim match, I'm gonna have to we're gonna ignore that, because you can't eclipse that, because it's first gonna get type checked in a way and reorganize a little bit when we actually go to implement that part. So that's just irrelevant to this. That doesn't participate in the system really. Okay, so now the only thing we're missing is StringCharSubtract, which I'm just going to implement right here. StringCharSubtract treats our string as a string set, so this is like A and B, and we're going to just say anything that exists in B should not exist in A. So this is going to be just dumb implementation. We're not going for we're not going for like some smart how'd you say it, like log n or linear, reduction of this. We're just going to do the basic n squared loop here. Keep using the wrong type of loop. There we go. Doesn't have j's in it yet. Size. Okay, so what we want to do is for everything in B, we're going to say eliminate that thing from A. Then what we're going to do is look at everything in A to eliminate it and say if a.stir I equals C, then a.stir I equals a.stir a.size minus 1, a.size minus equals 1, j minus equals 1. Well, that's going to be a problem because it's unsigned and I don't like screwing around with that, so we'll say j plus equals 1 here. If we get that far. And then this has actually got to be J's, so I got that wrong. So here what we're basically doing is saying if the thing we're looking at matches the thing we're trying to eliminate, pull somebody from later on back, because this isn't a real string, this is a string being used as a character set. So just pull someone else from the set back back to the slot to fill it in, and then reduce our size by 1. And if we do that, we want to not increment J because we want to check this character we just pulled back. If we didn't want to eliminate that, then just go ahead and increment. And once that's done, we should have a new A that is just the old A but modified. Now here's the problem. I don't really actually want to modify that string in place. So for this to actually work, what I'm going to need is an arena passed down to me. Or actually what I really will need is I'll need to make a copy of that here. So this is currently just saying give me the condition. What I actually want to do here is like say if you give me that condition, fine, but make sure that you actually copy the case characters into a separate copy so that we don't modify the original. I mean, let's think about that. Maybe we can use this as a way to optimize that as well, now that I think about it, right? I mean, there's no reason why we couldn't, now that I think about it. It's actually kind of handy that we're doing this, because not only can we remove redundant states, but states which have eclipted portions of their cases can be shrunk down to just the relevant section of their cases. So maybe I leave it exactly like it is, and I actually write the condition back. Whoops. I write the condition back at the end. Maybe that's how this needs to go. Right? That way the change in the string's size gets reflected back here. And we'll only do that though if we're actually preserving this transition in the first place. If this transition is getting removed from the state, then who cares? Alright, so yeah, that's good. Not sure where the 4coder slowness is coming from. Something weird is happening right there, and I don't know what it is, but this is an old version of 4coder, so it's not that surprising. It's just one I'm not used to since I haven't been using this version until very recently. Okay, anyway, point is, this should now become an optimizer, like a callable thing. So I want to pop over here. So there's my Eclipse opt simplify transitions, takes the Lexer primary context, and it goes to town on it like that. Opt simplify transitions context. Is that everything? Great. Alright, so there's one of these. That's happening. We want to do simplify flags as well. Yeah, that's not a bad thing to do next. So let's put that in right here. Again, we can do this. Well, let me think about that before I say it. So we have a flag set, and what we really want to do here is we want to iterate all of the you know what? There's no point in simplifying flags first anymore. The reason I originally said simplify flags first was to simplify, to shrink down the amount of memory it took to record the number, like the transition simplification, but that's not necessary anymore. So now I can start doing this like that. Okay. So more simplifications. We want to simplify states next. So how does that go? So to simplify states, first what I'm going to do is I'm going to have a thing that's like opt mark states mark all states excluded. So that, and then that'll also get combined with mark discard all excluded states. So this will just go ahead and exclude everything the way I'm writing it right there, but I just want to get those basic helpers in place first. So this is going to be opt mark all states excluded, and what that does is it loops the state set and for each state I'm going to set state optimized in to be false. Then discard all excluded states is one of these things that builds a new version of a list that already exists. So I need to grab the new list values here. I need one of these look ahead pointers. And then if the state is optimized in, which is, yeah, like this, optimized in, then we can push it onto the new list. Like that. Then when we're done, we reassign these like so. Right? So that builds a new list and stuffs it back into the states list for the context. But if I run that now, it's just going to make sure everything gets optimized out and actually lose behavior, right? It's going to lose the whole thing. It's not going to work. We're going to just optimize everything out. So now the question is, well, how do I make this actually do what I want it to do? All I have to do is make a system, make a procedure that's going to iterate the entire state machine, but only checking by only visiting states that you can actually reach from the root, right? And that looks like this. States, Lexer primary context. I'm just going to say that this actually starts by giving you a state pointer. Opt include reachable states. And so what we're basically saying is we could in theory start from any root and say like, hey, I want to include everything that this state can reach. And there might be good reasons at some point to have that as a feature in the future. For example, we might be in a situation where we have a sub-state machine that we know for sure is completely disconnected, but we are modeling it together with another part of the state machine that is, you know, going to be connected in some backhanded way that we can't, like, deduce from this, iteration we're writing here. Or that isn't even a part of the generator's output, it's actually part of something that gets hand-rolled or something, and you just don't want to have it optimized out, so you have some way of marking it as a new root. For now, we'll just say start from the only root we have. And all we do is this. We say, look, if this state is not already optimized in, then we do the following things. First, we say optimize this one in. Then we say iterate this state's transitions, because transitions are the only thing that indicate what possible states this state can move to. So I want to look at all of the transitions for this particular state. Right. And for each of them, I'm going to say, okay, call opt include reachable states on that state's on the destination state of that transition. So if anything has never been visited gets called here, it will come here, this will be false, and then it'll mark it as visited and start iterating all of its reachables, right? If it has been marked reachable, for instance, if I transition back to myself, which happens a lot for a lot of different things, or if I transition back to the root after emitting something, or if I transition to like if I transition to some other thing that has already been a part of a different branch, on all of those cases, it'll already have marked itself as optimized in, and it won't bother to do any more work for that one. So that is how we can visit all of the nodes in this, or all the states in the state machine, by treating the states as a graph and the transition rules as directed edges to walk the whole thing and optimize them all in. And now when we run this, we are only optimizing out states that are unreachable. Now that's probably not any of them if I'm not making any dumb mistakes in the model, but it's nice to have that code in there so that if I ever do want to write a state machine in a particular way that might be sloppy looking with extra states, because maybe there's like 2 different state machines that a particular piece of code helps to build, and some of the states in the state machine don't get used in both cases, right? They only get used in one case. That could happen, and then you have these states that are just sitting there that never actually participate. They just are there to say, hey, I was declared, but then I didn't end up being a part of the system because of the way things worked out. And that'll just clean that up. So that's cool. Okay, so we've simplified out the states. Now we want to say move all actions from state entries into the transitions. But the problem with that is if I do that right now, we're going to lose a few other pieces of information. Before I do that, what I actually want to do is transform all consumes, or we want to start by saying something like generate the base action list for transitions. And this is important because the way I actually describe things in the model, I don't actually ever talk about actions. Actions never get manually created except in one very specific case, and that's when I do stuff like the set flag on the entry of a state. This isn't actually generating an action and sticking it on the state. But this, for instance, is an emit rule. That's not the same thing as an action. The reason for that is that when I was building out the model, it was never really in my head that like, oh, whenever I do a transition, I want to list out the actions I do, and one of the actions is to do this emit. No, what I was thinking is like, okay, a case can do one of 2 things: change state, or it can go back to the root and in the process emit something. And so that's how I structured that. But it turns out that in addition to sometimes wanting to emit and sometimes not wanting to emit, there's also sometimes wanting to consume and not wanting to consume, and all that is encoded as like fields on a transition, right? There's like, do I consume input? The emit rule looks like it doesn't even get stored yet, which is weird. SM case. Maybe I didn't even finish the constructor as much as I thought I did. SMI case. What happens to the emit rule? Yeah, so the emit rule is not even becoming anything yet. So our emit rule is getting lost right here. The consume rule gets stored in a field, but then it gets lost and never gets put into the action set. So what I actually want to do here is I want to say, let's reconfigure as much as we need to this part so that we're actually generating an action list rather than just storing this. So like this, I think, is wrong. I think what we want to do is once we're constructing one of these case things, we want to right here build its action list and build it out of the consume rule and the emit rule right here, which are basically just treated as like particulars about a case, but are actually going to be transformed into generics about actions, right? The reason for that transformation is so that the decisions about when certain things need to happen can be made in a uniform way, so that all decisions about, okay, when does consume happen, before or after the emit? When does emit happen? Who do I transition to? What, like, series of things do I check when I'm trying to emit? Do I just do an emit, or do I do, like, this case and then this case and this case? Of, like, keyword checks? Do I do, like, when I do the transition to the next place, is that next place going to be something I can predict because I didn't do a consume, in which case I need to reorder stuff by pulling its stuff up into my list? Like, all of this is going to start becoming sort of a fluid concept of when certain actions need to be executed, and they're always going to occur on those transitions. So I want to start transforming things that were just sort of particular fields of a case handler into the actions that represent that. So it's kind of a midway point. The action list things are kind of like this midway point between the model I wrote and the model I'm like, and the generated code. It's a transform of model by a small like incremental amount, right? It's an in between. I don't know how else to put it. It's just a different data format that is easy to reach from the stuff I wanted to write by hand, and is easier to manipulate than the stuff I wrote by hand. Does that make sense? So I think we can, I think we can get this part. I think we can get this part started on the next video. So what we did on this video was I described basically the to-do list of things it's going to take to generate everything. We wrote the thing that simplifies transitions, figuring out the stuff about case eclipsing, and then we wrote the stuff that does state simplifying. And so the next big to-do item is I need to reconfigure my action list a little bit. Alright, so this was episode 2, and I will see you guys again on episode 3 in a little bit. Bye bye.